Alright. What we'll do now is to also talk about measures of variation for raw data. And realistically, for this class, we'll have just two measures of variation that are useful to us, and they're related to each other. One is called the variance, and in functionality it's related to, in concept, to the average. And related to the variance is a sort of more useful measure. That's the standard deviation. It's more useful because the standard deviation is in the same units of measurements as the average. And that distinction is useful sometimes when you're trying to get an idea of what the standard deviation is. So, we'll talk about sample only here. The sample variance, the formula for the sample variance is as follows. The notation is S squared is equal to the summation of the difference between each data point and the average squared, so the squared deviations, divided by not n but n minus 1. It's sort of difficult to describe what n minus 1 does for us. N minus 1, as we'll see way down the road in 215, is actually something called degrees of freedom, and it has to do with the fact that to estimate the sample variance as we're doing, okay, and we'll see later that's going to be an estimate of population variance. To do that, we need to know what the sample or population average is, and we estimate the population average with the sample average. So we use up one bit of data to do that. Anyway, it's a difficult concept, and even when we get to it later in 215 and describe degrees of freedom, it's not always clear that most students understand the concept or appreciate its importance. But anyway, it's we need to divide by n minus 1. The simpler way to calculate this is with the following formula: sigma x squared minus n times x bar squared, all divided by n minus 1. The first formula, you'd have to first find the average, and then as a second part of the problem, you'd have to find the differences between the x's and the average, which need not be very nice numbers, square those differences, etc. In the second formula, actually we can go through the data sort of once, do a couple of calculations at the same time, and go from there. Even for a computer, the second formula is more important. Alright, and then the sample standard deviation. It's just S, which is hopefully clearly just the square root of the variance. Alright, some students ask why do we need both of these? Yeah, for a lot of our uses, all we'll require for calculations and for probabilities down the road, or for other things, we'll need the standard deviation, but clearly the variance is required along the way, and the variance has sort of entered the statistician's jargon as a sort of generic but most important measure of variation. So since we need to calculate it along the way, and since it's important in the statistical jargon, we'll use that notation. Alright, so let's go to our original data set. Let me get a new page here and write up our data. I'm going to put it in tabular form, so we'll have a column for our x's. Alright, so put it in the original order, not that it matters. Alright. Alright, and then we'll have a column for x squared. Alright, we add the x's, which we've done before. That's 12, and that 12 is called sigma x. We get the x squared, so we get each of the x's and square them. Alright, 0 squared is 0, 1 squared is 1, 2 squared is 4, 4 squared is 16. Alright. And then we add up the x squareds. We'll find that's 30. And the notation given to that is sigma x squared. Notice that sigma x squared is not equal to sigma x squared. Alright, so our sigma x squared is 30, is not equal to the 12 squared, 12 squared being 144. Sigma x squared is only equal to the sigma x all squared in very strange circumstances, that is where all the values are equal to 0. And of course sort of a strange situation to be in. Alright, so remember our x bar, sigma x divided by n, is 12 divided by 10 is 1.2. So this is the average or mean. The variance, s squared, is sigma x squared minus n times x bar squared divided by n minus 1. Sigma x squared is the 30 minus n, 10 data points, times x bar 1.2 squared divided by n minus 1. Alright, that boils down to 1.7333, actually 3 recurring. In our calculations we will round to what are called 4 significant places. Alright, so this particular number, 1.7333, and that goes on forever. Alright, we come from the left hand side, we don't worry about decimal places or anything. We start counting. This is the first significant place, second, third, fourth significant place. Then we look at the numbers beyond that. If it's greater than or equal to 5, we round the fourth place up. If it's less than 5, we what rounds down, we keep it the same. So in this case, the fifth place beyond is less than 5. So to 4 significant places, we have 1.733. But remember, we will use at least four significant places. So if you want to be more accurate than that, that's fine. Alright, so sample variance 1.733. The sample standard deviation S then is the square root of the variance Alright, and the answer to that is 1.317. Okay, it'll take a while to get used to the sizes of the standard deviation, but remember this is in the same unit of measurement as the data. So if our data was the number of items, number of houses sold per month by a real estate agent, the S is also the number of houses sold per month. So the variation is measured in those units. So on average, the average deviation from the average of 1.2 is about 1.3. So sometimes it'll be 1.2, the average, minus 1.3, alright, just below 0 or 0. And sometimes it'll be 1.2 plus 1.3, alright, get you at about 2.5, okay. Of course you can't sell 2.5 houses, so it'll be 1 or 2 or 3 or whatever. Alright, so now we've covered the basic measures of central tendency, mean, median, and mode, and the basic measures for variation, the variance, and the standard deviation.